Hello everyone, I'm Arpit. Today I will be presenting SQL Check, a tool chain for detecting and fixing anti-patterns in SQL applications. This is joint work with my colleagues Prashanth and Joy from the Georgia Tech Database Group. Today, building and deploying database applications is easier than before due to the availability of frameworks, ORMs, and database as a service platforms. However, it is still challenging for a developer to avoid certain anti-patterns while choosing the logical design, physical design, and queries of the application. So, what are anti-patterns? They are accidental design decisions made by the developer without understanding the principles of database management systems. They end up negatively affecting the performance, maintainability, and accuracy of the application. Here's an example. Consider a movie database application where we have a collection of movies and actors. An actor can act in multiple movies. In database terminology, this use case represents a many-to-many relationship. Let's look at an easy schema to represent this many-to-many relationship. We have an actor table that stores information of all the actors and a movie table that stores movie information. In the movie table, we can store a comma-separated list of actor IDs to represent the many-to-many relationship. Given this schema, we will look at an example task. Let us say we want to get a list of all the movies in which Kate Winslet acted. Given our database design, we can execute a query that joins the movie and actor tables either by using a join condition that uses complex pattern matching or by using a string processing technique like splitting for checking the join condition. It can be seen that the choice of our design increases the complexity of the predicates. This complexity arises because the developer decided to use a comma-separated list to capture the many-to-many relationship. Now, let us look at an alternate design that fixes this anti-pattern. Similar to the previous design, we have the movie and actor tables. However, instead of using a comma-separated list, we represent the many-to-many relationship using an intersection table. If we perform the same task with the new schema, the query complexity reduces, allowing the DBMS to perform join optimizations. Performance-wise, this query executes 636 times faster on a dataset with 10 million records. As we illustrated in the case study, an anti-pattern can negatively impact the performance of the application. Besides performance, anti-patterns can also affect the maintainability, data integrity, accuracy, and storage footprint of the application. To mitigate the impact of these anti-patterns, we developed SQL Check, a tool chain that automatically detects potential anti-patterns in the application's schema and queries, helps repair the detected anti-patterns by suggesting fixes, and ranks the anti-patterns based on their impact. Architecture-wise, SQL Check takes as input a set of SQL queries from the application's query log and optionally a connection to the application's database. The detect module uses these inputs to identify the anti-patterns that are then ranked and repaired to eventually return the fixes to the user. The detection component of SQL Check contains two modules, query analysis and data analysis. The query analysis module analyzes SQL queries executed by the database application. It detects anti-patterns using two different algorithms, intra-query detection and inter-query detection. With intra-query detection, it applies a set of rules on each SQL statement one at a time. Let's look at an example. Given the movie table, we want to retrieve the name and unique ID of movies which were released in the year 1997. We can get this result using this query. However, we observe that the result set contains extra columns that are not required. This happens due to the usage of a wildcard in the query. A detection rule identifies this wildcard and returns the column wildcard usage anti-pattern. In this manner, the intra-query detection algorithm identifies many anti-patterns. However, it cannot detect more complex anti-patterns that require the application's context. To detect these complex anti-patterns, as well as to reduce the number of false positives and false negatives, the detection component utilizes the inter-query detection algorithm that uses the entire application's context, consisting of other SQL statements and the database schema, For example, consider the create table statement for the movie actor intersection table. We do not observe any obvious anti-pattern in it. However, if we look at the application's context consisting of another query, we see that the movie ID of the movie actor table is being utilized in the join predicate. From this, we can infer that a foreign key constraint is missing in the application. Besides looking at the application's queries, the detection component also looks at the data. The data analysis module utilizes the metadata of the database tables, such as column data types, and the distribution of data present in the database columns, such as range and unique values. Consider the multi-valued attribute anti-pattern discussed before. It is not always possible to detect this anti-pattern using only the application's queries. To detect this anti-pattern, SQL Check first identifies the data type of each column using the schema information. It then samples a few records from the columns that are of text type. Finally, it applies a data rule on the sample data to detect multiple commas in each value and therefore marks it as a possible candidate for the multi-valued attribute anti-pattern. Leveraging both query analysis and data analysis, SQL Check detects four categories of anti-patterns: logical design, physical design, query, and data. In total, SQL Check currently detects 26 types of anti-patterns. Merely detecting high-impact anti-patterns will not be sufficient, as users of SQL Check might not be familiar with the anti-pattern and how it can be fixed. For this purpose, SQL Check provides a repair module, which provides application-specific suggestions for fixing the anti-patterns. The suggestions provided by SQL Check are a combination of textual explanations and rewritten SQL statements for fixing the anti-pattern. Here's an example. Consider the multi-valued attribute anti-pattern. To repair this anti-pattern, the developer should create an intersection table. In this case, SQL Check provides the SQL statements that must be executed to achieve this transformation. First, it suggests a create table statement for generating the movie actor's intersection table. The developer must then manually transform the comma-separated lists in the actors column to generate data for the movie actor table. Lastly, SQL Check provides an alter table statement for dropping the actors column, concluding the fix. It is not always possible to rewrite the SQL as it might require application-specific knowledge or several complex transformations. In this case, SQL Check only provides application-specific textual fixes. Consider the column wildcard usage anti-pattern. Here, the developer must rewrite the query to only fetch the required columns in the projection list. However, SQL Check cannot automatically rewrite the query since it requires application-specific knowledge. Therefore, instead of rewriting the query, SQL Check provides textual feedback along with the list of columns in the movie table. It is possible for large applications to have many anti-patterns. This makes it cumbersome to go through each anti-pattern and fix them. To prioritize the developer's attention, SQL Check ranks the detected anti-patterns based on their impact. For each anti-pattern, SQL Check uses 6 metrics for computing this impact score: read and write performance, maintainability, data amplification, data integrity, and accuracy. We evaluated SQL Check on many real-world applications. To evaluate the detection component, we compared SQL Check against DBDO, the state-of-the-art anti-pattern detection tool. Unlike SQL Check, DBDO neither ranks anti-patterns nor suggests fixes for repairing them. To evaluate the ranking and repair modules, we set up a real-world application with synthetic data to evaluate the performance impact in terms of query execution time with and without anti-patterns. We also conducted a user study to measure the efficacy of SQL Check's anti-pattern fixes. I will next present the results of these experiments. We first downloaded 1,406 open source repositories from GitHub and extracted 174,000 SQL queries. We ran these queries through both SQL Check and DBDO and found that unlike DBDO, which only supports 11 types of anti-patterns, SQL Check supports 21 types of anti-patterns. SQL Check detects 4 times more anti-patterns compared to DBDO. It returns 48% fewer false positives and 28% fewer false negatives compared to DBDO. We attribute this to the interquery and data analysis algorithms that leverage the application's context to deliver higher precision and recall. To evaluate the ranking and repair modules, we set up global leaks, an open source whistleblowing application, and loaded 10 million synthetic records. We then compared the execution time of the statements with anti-patterns versus the fixes suggested by SQL Check. For the multi-valued attribute anti-pattern, we found that fixing it improves performance by 636 times for a select statement, 193 times for an insert statement, and 256 times for a delete statement. We conducted a user study where we tasked participants to develop an e-commerce application from a given set of requirements. 23 participants who were graduate students studying computer science reported an overall efficacy of 67% for SQL Check's anti-pattern fixes. The overall feedback was positive and encouraging. One participant accepted that they should have used numeric instead of real as the data type. Another participant rejected the column wildcard usage anti-pattern as they really wanted all columns, even questioning the existence of select star. We also evaluated SQL Check against many Django-based repositories on GitHub and SQLite databases on Kaggle. We have opened issues on the GitHub repositories to report these detected anti-patterns. Developers have acknowledged many of these anti-patterns and have already fixed a subset of them. We have deployed SQL Check as a service at Georgia Tech. We hope that it will benefit both beginners and experienced application developers. We would like to acknowledge our sponsors for their support. We would also like to thank the application developers and colleagues for their helpful feedback. With that, I would like to conclude my talk. Thanks for your time. We will be happy to take questions.